Hello and welcome back. Welcome to part 3 of this video series, Introduction to Convolutional Neural Networks. In previous part, we saw the operation convolution in detail. We also implemented that in Python, and we saw how convolution can be viewed as a perceptron obviously with an activation function. And we also saw how convolutional neural network actually reduced the number of parameters by parameter sharing, thereby avoiding overfitting. In this particular part of this video series, we basically move further and we will discuss some of the terminologies related to the architecture of CNN, which is one of these things are basically filter banks. What do we mean by a filter bank? What is padding? What is stride? What is pooling? What do we mean by tensor and volumes and stuff like so? So let's dive in and see one by one these terms. So one basic term that you may encounter is filter bank. Normally what happens is a filter or the convolution mask. You can also call that as a mask bank, but the most famous term is the filter bank. A filter basically is a mask. That's simply a mask. When we call as filter bank, that means we have several masks. So that is mask 1, that is mask 2. We may have several masks, that is mask 3 and so on. We may have K masks, MK. In this particular example, that's our input structure. I'm avoiding the term image again and again. I'm calling that as a structure. I should call that as a tensor, but I will define tensor later on in this part. So until then, I'm calling that as a structure. I'm avoiding that term because in the very input stage, in the first stage, that may be an image, but in the layers in between, that may not that may be different than an ordinary RGB image. It may be a different thing. That's why I'm calling that as an input structure. But if you're comfortable with image, that's perfectly okay. So that's our input. And here we have in our filter bank, we basically have two filters. This is filter 1, which has the filter itself is 3 by 3, and the total number of channels of the filter is the same as the total number of channels of our input structure, which is 3 in this particular case. That's our first mask. And in our filter bank, that's our second mask, or that's our second filter, which again has the same size as 3 by 3, and the total number of channels are exactly the same as original one. So that's our filter bank. We may have another filter in our filter bank in this particular stage that might be 3 by 3 by 3 matrix, like so, and that might be a third filter in our filter bank. But in this particular case, we have two filters. When we convolve or we apply this filter on this particular structure, we actually get a 4 by 4 mask out of it, assuming that's a 3 by 3 image. So let me go over this. So we first go to this pixel, then to this pixel, then to this pixel, and then to this pixel, assuming we are not going out of the boundary. Then we go to this pixel, computer number, then we go to this pixel, computer number, we go to this pixel, computer number, and this one. Similarly, all these numbers that I have, all these locations that I've highlighted, upon these the filter is applied, assuming we are not going out of the boundary. So the result becomes a 4 by 4 matrix after this filter is applied. Similarly, when this filter is applied, another 4 by 4 result is carried out. So the filter bank basically is the total number of filters you have, and normally the total number of channels of a filter is the same as the total number of channels of your input tensor or input structure, in this particular case input image, and you may have several of such filters. Each filter is maybe independent of the other filter. Then what happens in CNN is you have two responses. This filter has this particular response, and this filter has this particular response. You actually pass these responses through an activation after adding a bias in it. There is a particular role of bias that actually is there. So you add a bias, then you apply activation function, and after the activation function, you have the result of this first filter and the result of this filter. When you apply this activation, that becomes a perceptron. And then you can arrange these responses again in a multidimensional way, and that's your output of these two filters. And then you may have another layer here. For example, you may have a 3 by 3 by 2 a filter. Then you may have another filter which is 3 by 3 by 2, or the size may be other than 3 by 3, maybe a different one, and you move on. So the idea of filter bank basically is how many filters do you have at each layer, and in different layers you may have different number of filters. Next, we talk about padding. As you have seen in the previous slide as well, what if I want to utilize this information as well? What if I place my filter exactly at this particular location? Then what happens is some of the boundaries will go out. So for example, if my mask is 3 by 3 and this is the center of the mask, then if I place the center here, then obviously there are certain pixels that will be out of this boundary. So what happens normally is one workaround is to pad your original image with zeros around the image and pretend that is also part of the image, and then place your center, the center of the mask on the original pixel or the original value, thereby avoiding the kind of implementation hassles. So one way of avoiding this problem is padding with a particular number constant. Normally that number is 0. Another way is to apply symmetric reflectance, for example, and padding. How much padding do you really want? It basically depends. If you want your output size to be the same as the input size, this is the input size. If you want your output size to be exactly the same as the input size, you can exactly define how much padding do you really want. And padding can be by a fixed number, or padding can be by symmetric reflectance. By symmetric reflectance, I mean, for example, if you have these numbers 1, 2, 3, 4, and then you have 6, 1, 1, 4, let's say, then you may, if you are applying padding by 2 with symmetric reflectance, what will happen is the following. So this will copy here 1, 2, 3, 1, 2, 3, 4. That is the image of this particular thing. And then this 6, 1, 1, 4. Like you can think that there is a mirror here, and this is reflected across this mirror, and that is called the symmetric reflectance that we also saw in the Python code in the previous video, where we set our boundary parameter as symmetric. Remember that? That is highlighting this symmetric reflectance. There are a couple of ways of doing this padding, but the essence of that, how much padding do you want, basically tells what will be the size of the output. And normally the padding is decided in a way that the output stays the same, or if you do not pad, then the output shrinks by a particular amount. Other than padding, there is another term that is closely related, which is called the stride. What happens is if you, for example, slide your mask over your input image or input structure, then you can, for example, if you have a 3 by 3 mask and you have placed the center over here, the next center can be placed over here, which means you can just slide over 1 pixel, or you can jump, for example, 2 pixels just to reduce the size of the output. You can rather than jumping by pixel 1, you can jump by multiple pixels, and that by reducing the output size. And you can decide this particular parameter, which is called the stride parameter, to reduce the size. Obviously there is no fixed stride parameter that you should use. That's a hyperparameter, and the best numbers can be learned through the data. But deciding this number other than 1 allows you to jump larger pixels or larger jumps in the X direction as well as in the Y direction. For example, in this particular case, the stride value in X direction or in this particular direction is 2, which means skip every pixel or take the jump of 2. And the stride in Y is also 2, which means if the input image is 1, 2, 3, 4, 5, 6, 7, if the input image is that, the output image will be half of that in each dimension. So yeah, so you do this, then you take rather than taking 1 pixel, you jump 2 pixels and you move there, then you place there. Now from here, rather than taking 1 pixel, you take 2 pixels and you go there. Then going down, rather than jumping 1 pixel, you jump 2 pixel and place here. Then rather than going here, you go this, and that is called a stride. Stride reduces the dimensions of the output, and for a desired output, you can actually come up with exact parameters. How much padding do you decide and how much stride you set, that actually give you the exact dimensions of the desired output, and that's the hyperparameter. There is no fixed number, although there are rules to set particular kind of stride parameters, but at the end of the day, that's a hyperparameter. If you go to TensorFlow, for example, TensorFlow allows you to set the padding and stride parameters when you are designing layers, when you're designing convolution layers. Next, we talk about pooling. So pooling is basically, for example, if with a 2x2 pooling, if that's a result of, so think about applying an activation function and the result is out. So after this result, after applying up the activation function, if you do a max pooling, for example, a 2x2 max pooling, by a max pooling, a 2x2 max pooling, I mean you pick a 2x2 structure and pick a max of that. In this particular case, this is 20. Then you pick another 2x2 structure without any sharing, and you pick a max of that, that is 30. And then you pick a max of this, which is 112, and then you pick a max of that, which is 37. So that is max pooling, which further reduces the, so if you set the stride up, that reduces the output dimensions. If you apply the max pooling with more than 1 by 1, that also basically reduces the size of output. But the point of having the pooling layer or the pooling function is not just to reduce the size. It has a very close connections to our biological systems. For example, in Wiebel and Husel, they actually come up with an experiment, and after that in 1980s, the experiment was improved. And what they discovered is actually the perceptrons, different perceptrons, they actually are looking on the regions of the eye, the visual cortex, the eye. So if that's the eye, if that's the retina, then each neuron, rather than seeing the whole information, it is seeing actually a region of the information. And that's where basically the term convolution, people think about convolution. So why not we design neurons that actually see the regions of the input rather than the whole region? So these kind of cells, they term those cells as S cells or simple cells. And there can be many such cells, so many S cells. Then what they discover, there are other cells called C cells that somehow validate that information by a sort of voting or max voting. So what they discovered, that the C cells, also called complex cells, they deploy some kind of voting mechanism or max voting mechanism to basically clarify the information gathered by this S cells. So so that's where this convolution basically, because if you have an image, you actually see different regions of those, and each region can be modeled, as we saw earlier, as a perceptron. In the previous part, we saw the convolution for each region can be modeled as a perceptron. So that is where these S cells are generated, and this max pooling is applied on basically the activations of these S cells, which normally is what they discovered is kind of max voting. So this pooling and convolution both are biologically inspired, and it turns out that if convolution layer is followed by a pooling layer, then it is more close to what biological brain actually does, which might be thought of as a benchmark. Other than max pooling, people also discovered like average pooling and other kind of pooling techniques as well. Then we saw tensors. A tensor is a very kind of casual definition of a tensor is it's a multi-dimensional matrix. Multi-dimensional array. Let me call it an array. So for example, that's a 2D array, and this is called a matrix. If you have array of such 2D arrays, that is called a 3D array or a 3D tensor as well. If you have an array of these kind of structures, so array of this, so that is called a 4D tensor or 4D array or 4D tensor. And if you have an array of these kind of structures, that's a 5D tensor and so on. So tensor is a fancy name of a multidimensional array. So what happens normally is in between the layers, you have tensors, you have filter banks. Each element of the filter banks are also tensors. And when you convolve them, you get other tensors. And in backpropagation, actually we forward these tensors in the forward direction in the forward pass, and we move those tensors in the backward direction in the backward pass, and that's where the term tensor flow might be inspired of, because the tensors are flowing back and forth. So the architecture of CNN, basically you have input image normally or input signal in general. Then you have convolutional layers, and then you have this subsampling or pooling layers. Then you may have other convolutional layers. Then you have pooling layers. Although the biological systems, they actually guide that every convolution layer actually should be followed by a pooling layer, but in practice, this can be altered, and people came up with altered architectures as well. And also the biological system says that there is only one convolution and only one max pooling layer. But in practice, people deploy several convolution and pooling layers in a cascade or a series manner. And further, it is not necessary to always deploy a pooling after convolution. And I mean, this is all the architecture you can play with, and which architecture is the best, how many filters in a filter bank for each layer should be there. These are all hyperparameters. And I mean, there is no quick or there is no optimal answers to that. It is only overtraining and maybe cross-validation to come up with better answers for these. So once you have your convolution architecture, which is sometimes called the feature extractor, which extracts the features for these kind of filters through backpropagation, obviously, then at the very end, the final tensor actually is flattened out, and after that, an ordinary MLP or multi-layer perceptron is carried out, and the loss at the end of the day is computed exactly like in the ordinary MLPs, and that's how the convolutional neural network plays. One difference is that in the convolutional neural network, the filters or the mask, unlike the classical computer vision techniques, the values in the masks, they are parameters. They are not fixed values. They are not hand designed. Rather, they are learned to best represent, to best minimize this particular loss at the end of the day. That's why the convolutional part is also can be known as feature extractor or feature learner that learns the best features. So that's about it. If you, for example, want to implement a convolutional layer, a convolutional neural network in TensorFlow, we already have a YouTube video in the topic Introduction to TensorFlow. So please go and see the third video of the TensorFlow on AI Sciences channel at YouTube. And there we have implemented convolutional neural network in TensorFlow in the Google Colab. And if you want to see more theoretical and practical and more Pythonic details of convolutional neural networks, then please do enroll to our full course on convolutional neural networks at AI Sciences. So where we have explained all these terms bit by bit along with their implementations in Python. So if you like this content, please press the like button, subscribe our channel, and share to your fellows, and hope to see you next time.